Welcome to the Deep Dive. Today, we're tackling something really key for understanding, well, the job market, how it swings up and down. We're looking at how economists try to model unemployment accurately.
Mm-hmm.
Forget the simple takes. We're going deep into the Diamond-Mortensen-Pissarides model, the DMP model.
That's right. It's pretty much the go-to framework for economists studying this stuff.
So for you, the learner, this is really about getting a clearer picture, a more realistic one, of how labor markets actually work and react to changes in the economy.
Yeah.
We're moving beyond the sort of simplified stuff.
Exactly. Think of it as a shortcut to the sophisticated analysis, without getting bogged down in super dense academic papers. We're pulling out the crucial insights to show why the way you analyze this matters and what simpler ways might be missing.
Couldn't have said it better. Our main source here is a research paper, a really solid one, called Solving the Diamond-Mortensen-Pissarides Model Accurately.
Right, by Nicholas Petrosky-Nadeau and Lou Zhang. It was published in Quantitative Economics.
And that title, Solving Accurately, kind of gives the game away, doesn't it? It's all about the methods. How do we actually solve this important DMP model properly? So our mission today is to figure out why using these accurate, non-simplified techniques is so vital, and what important things about unemployment they show us. Things the simpler ways might, well, hide.
Yeah, and there might be some surprising findings along the way, but first, maybe we should establish just how important this DMP model actually is.
Good point. It's not just an idea. It's described as the dominant framework for thinking about the labor market and equilibrium unemployment.
It really is. It's woven into so much of modern macroeconomics. The paper mentions its use in understanding business cycles.
Yeah, the booms and busts. Think MERS back in 95, Andelfado in 96.
Right. And it's also core to new Keynesian models, the kind central banks often use. Gertler and Trigari looked at that in 2009.
It pops up in thinking about monetary policy itself, too, like Blanchard and Gawley's work, and even surprisingly in studying big sort of disaster shocks to the economy.
That was Petrosky-Nadeau, Zhang, and Kuhn in 2015. Yeah. So you see, getting this model right has huge implications across economics.
Absolutely. It's like the bedrock for a lot of labor market analysis.
Okay, so given it's so central, economists obviously use it a lot to understand real-world job numbers, especially how unemployment bounces around. But here's the twist. For a long time, a very common way to handle the DMP model involved, well, simplifying the math, a technique called log linearization.
Okay, log linearization. Let's unpack that. What is it, roughly, and why does this paper suggest it's maybe not the best approach?
Well, fundamentally, log linearization is a way to make these often very complex economic models mathematically easier to handle. It works by focusing on how the model behaves very close to its long-run average or its steady state.
So it simplifies things by assuming the economy doesn't stray too far from this average point.
Exactly. It assumes small deviations, and that makes the calculations much simpler. But as the paper argues pretty strongly, this simplification comes at a cost, especially for the DMP model.
Right, like trying to understand a whole mountain range by just looking at a small, flat bit of ground near the base camp.
That's a great analogy, actually. It focuses on the local dynamics and can miss the bigger picture, the really dramatic ups and downs.
So what specific problems did Petrosky-Nadeau and Zhang find with log linearization when they compared it to more accurate ways of solving the model? What did it get wrong?
Okay, the findings are pretty stark. First off, log linearization seems to underestimate both the average level of unemployment and how much it swings around its volatility.
Underestimates both. Okay.
Yeah. They used the Hagedorn and Manovsky model from 2008 as a test case. With log linearization, they got a steady state unemployment rate of about 5.3%.
Okay.
But solving it accurately pushed that mean unemployment rate up to over 6.1%, almost a full percentage point higher.
Wow, that's not trivial. What about the volatility?
Big difference there, too. Log linearization gave a volatility measure of 0.133, the accurate solution. 0.258, nearly double.
Nearly double. So it makes unemployment seem much more stable than the model actually implies when solved properly.
Precisely. Interestingly, the paper notes the actual U.S. data volatility is around 0.125. So neither method perfectly matches that specific number, but the accurate method captures much more inherent volatility within the model.
Okay, so it understates the average level and the swings. What else?
It also seems to overstate how much labor market tightness fluctuates.
Tightness. That's the ratio of vacancies to unemployed people, right? How easy it is for firms to find workers or workers to find jobs.
Exactly. Think of it as the job market's matchmaking efficiency. Log linearization predicted a volatility for tightness of 0.327, but the accurate solution found it was lower at 0.267.
So it gets that wrong too. And the relationship between unemployment and vacancies, the Beveridge curve.
Yeah, it messes with that too. Log linearization found a very strong negative correlation, minus 0.848.
Amazing.
Very tightly linked. The accurate method found a much weaker connection, only minus 0.567. So the simplified method suggests vacancies and unemployment move in almost perfect opposition, while the reality, according to the accurate solution, is looser.
Okay, so it's not just getting the levels and volatility wrong, but the fundamental relationships within the labor market. How does this affect understanding actual economic events, like recessions?
This is where it gets really crucial, I think. The paper shows log linearization significantly understates unemployment's response during bad times.
Okay.
So imagine a negative productivity shock hits a weak economy. Log linearization predicts unemployment only goes up by about 0.33%.
A tiny blip.
Yeah, but the accurate solution, it shows unemployment jumping by 1.35%. That's more than 4 times higher.
Goodness. So policy decisions based on the simpler model might have seriously underestimated the impact of downturns.
It certainly raises that possibility. And conversely, during booms, log linearization overstates how much the market tightens when things get better. In response to a positive shock in a strong economy, it predicted a big surge in market tightness, like 2.38. But the accurate method showed a much more muted, gradual increase of only 0.168.
So the simple model makes booms look perhaps frothier in the labor market than they might be, according to the accurate solution.
Exactly. It suggests a much faster response of vacancies than the accurate model implies.
So the simplified model is basically smoothing everything out. It misses the sharp pain of recessions and maybe exaggerates the frenzy of booms. Why? What's the underlying reason log linearization fails here?
The fundamental reason is nonlinearity. Unemployment doesn't just move up and down in a nice, simple, straight line relative to economic shocks. Log linearization, because it focuses only on that small area around the steady state, it essentially forces the model to behave linearly.
And reality isn't linear.
Not at all, especially not unemployment. The paper uses this really good analogy, the congestion externality.
Congestion, like a traffic
Yeah,
jam.
sort of, but for jobs. In a recession, you have loads of unemployed people looking for very few jobs. So even if more people become unemployed, the rate at which firms can actually fill those few vacancies doesn't really increase much. It hits a kind of ceiling.
Okay. The bottleneck effect again. Adding more job seekers doesn't speed up hiring if there are hardly any jobs.
Precisely. And that limitation, that nonlinearity, causes unemployment to spike sharply. Now flip it. In a boom, you have lots of vacancies chasing relatively few unemployed workers.
Right.
Here, adding just one more vacancy makes it noticeably harder for all firms to hire someone. The cost of finding a worker goes up quickly for everyone. This acts like a brake, slowing down how quickly unemployment falls.
So unemployment shoots up fast in a bust, but comes down more gradually in a boom because of these different congestion effects at the extremes.
Exactly, and these crucial nonlinear dynamics are just, well, they're largely missed by a linear approximation, like log linearization.
Okay, that makes a lot of sense. Now, the paper also mentions another approach, second-order perturbation in logs. Is that any better? It sounds a bit more advanced.
It is slightly more advanced. It tries to capture some of the nonlinearity by adding, well, a second layer to the approximation, going beyond the simple linear term.
Does it work?
It helps a bit, sometimes. In that Hagedorn-Minosky model, the paper finds it does improve things compared to basic log linearization. It gets closer on unemployment volatility, for instance, and the unemployment vacancy correlation.
Okay, so a step in the right direction.
A small step, maybe. But the really crucial finding is that when you move to more complex, richer models, the paper uses an example from Petrosky-Nadeau, Zhang, and Kuhn from 2015, which includes things like capital investment alongside the job search stuff.
Right, more moving parts.
In those cases, second-order perturbation can apparently produce results that are, and this is a quote, wildly inaccurate.
Wildly inaccurate. Why?
Because these richer economies can, in the model, swing much further away from their steady states. The second-order adjustments, which are still calculated locally around that steady state, just aren't enough. They break down. The paper talks about large Euler equation errors.
Which basically means the model is giving inconsistent predictions about rational behavior, right?
Essentially, yes. It's a sign that the approximation method is really struggling to capture the true dynamics of the model when the economy moves far from its average state.
Okay, so If log linearization is too simple, and even second-order perturbation isn't reliable for complex models, what's the answer? What are these accurate global algorithms the paper promotes?
They advocate for using what are called projection algorithms.
Hmm.
These are fundamentally different. They are global methods.
Global.
Meaning instead of just focusing on that tiny area around the steady state like the perturbation methods do.
The flat bit of the roller coaster track.
Exactly. Projection methods aim to find the solution across the entire relevant range of economic conditions the model can experience. They try to map the whole track, the ups, the downs, everything.
Ah, okay. So they don't rely on those local approximations. They try to get the full picture.
That's the idea. They are designed to capture those nonlinearities that the other methods miss.
And how did these projection methods fare when applied to the models in the paper? Let's start with Hagedorn-Minovsky again.
Well, applied there, they confirmed what the problems with log linearization suggested. They found significantly higher unemployment volatility, that 0.258 number we mentioned earlier,
Right.
and that notably weaker unemployment vacancy correlation, the Narishino 0.567, much less tightly connected than log linearization suggested.
And did they show those nonlinear responses, the sharp rises and gradual falls?
Clearly, the impulse responses generated using projection methods showed exactly that. Unemployment spiking much more in response to negative shocks, and market tightness rising much more gradually after positive shocks. It captures that asymmetry.
Okay. And what about the more complex model, the PZK model with capital and search? Did projection methods make a big difference there too?
Oh, absolutely. Even more dramatically in some ways. The average unemployment rate found using projection methods was way higher, 10.75%.
10.75. Compared to what from log linearization?
It compared to just 5.75% from log linearization, a huge difference in the model's implied long-run unemployment level.
Wow. Okay. What else?
Yeah, they also found higher volatility for other key things like economic output growth, consumption growth, investment growth. Everything was generally more volatile than log linearization suggested.
So the accurate solution paints a picture of a more volatile economy overall.
In that model, yes. And again, consistent with the simpler model, they found a weaker unemployment vacancy correlation, a nudge 0.359 versus narrow 0.536, and those same asymmetric dynamics. Stronger unemployment jumps in recessions, slower tightness increases in booms.
And crucially, I guess, the projection method didn't suffer from those wildly inaccurate results or large errors that the perturbation methods did in this complex model.
Exactly. The paper points out that the Euler equation errors associated with log linearization and second-order perturbation were very large in the PZK model, underlining just how poorly those methods performed when the model got more complex and realistic. The projection method avoids those pitfalls.
It really sounds like these global methods are essential for getting a trustworthy look, especially with richer models. Now, one more technical point the paper raised, something about discretization methods. Ruwenhorst versus Tauchen, what's that about?
Right. So when you use these projection methods, you often have to deal with economic variables like productivity that economists model as evolving continuously over time, but perhaps randomly.
Okay.
To solve the model on a computer, you usually need to approximate that smooth, continuous process with a finite number of discrete states or points on a grid. That's discretization.
Like turning a smooth ramp into a set of stairs.
That's a decent way to think about it, yes. And the paper looks at two popular ways to build those stairs: the Ruwenhorst method and the Tauchen method.
Doesn't matter which staircase you build.
Apparently, yes, it can. The paper finds that the Ruwenhorst method generally delivers more accurate and robust results, especially when the underlying process you're approximating is highly persistent, meaning shocks tend to hang around for a while, which is often thought to be true for productivity.
So Ruwenhorst is better for sticky processes.
It seems to be less sensitive to the exact number of stairs you choose, or where you set the top and bottom steps, compared to the Tauchen method. And they make an interesting point. Hagedorn and Minovsky, in their original 2008 paper, used the Tauchen method.
Ah, so some of the differences in results might even come down to that technical choice of discretization, not just the main solution algorithm.
It's a contributing factor, potentially. It highlights that even within the more accurate global approach, these finer details of implementation can matter. It's about getting the whole process right.
Okay, this has been a fantastic deep dive into the mechanics. So let's bring it back to the learner. What's the single most important message to take away from all this?
I think the core message is How we solve these economic models, especially something as central as the DMP model for unemployment, really truly matters. It's not just a technical detail for academics.
Right.
Relying on simpler methods like log linearization can give you a fundamentally misleading picture of how the labor market actually behaves.
Misleading in what ways, just to recap?
Well, they tend to understate how high unemployment usually is and how much it fluctuates. They overstate how volatile market tightness is, and they get the connection between unemployment and vacancies wrong.
Mm-hmm. And
crucially, they smooth out those sharp, nonlinear movements. They miss the severity of unemployment spikes in recessions and the more gradual recovery during booms. These nonlinearities seem to be a core feature of the actual labor market.
and even slightly fancier approximations like second-order perturbation can fall apart in more realistic models.
Exactly. The accurate global methods like projection algorithms, while more complex to implement, seem necessary to capture these vital dynamics and give us a more trustworthy understanding.
So here's maybe a final thought to leave you, the learner, with. If our historical understanding and maybe even policy responses related to unemployment have sometimes relied on insights from these simpler, potentially misleading models, well, how might that have shaped our view of past recessions or booms? And how might it affect our predictions or preparations for the future of the job market? It really underscores the need to look under the hood of the economic analysis we see, doesn't it?
It absolutely does. And for anyone wanting to, dig even deeper, exploring these global solution methods further, or looking into the real-world consequences of these nonlinearities, or even the details of model calibration, there's certainly a lot more there.
Yeah, definitely fertile ground. Well, thank you for joining us on this deep dive into getting the models right. It's certainly shown why accuracy is paramount when studying something as vital as unemployment.
My pleasure. It's a fascinating and important area.